Hello everyone, and welcome to Fluids Today. I'm your host, Taylor. We love to break down super awesome fluids concepts, and today we have with us Professor Moore, who's going to give us a little treat today.
That's right, Taylor. Today we'll be talking about Bernoulli's equation and how we can use it to explain how lift works.
That's great, Professor. Now, what should our students, especially those of high school age, be able to take away from this?
Well, Taylor, they should be able to take away these things.
So how can we explain lift?
You can explain a plethora of fluid phenomenon using Bernoulli's equation and predict the behavior of fluids such as air. Let me explain Bernoulli's equation. Here we have the pressure form of Bernoulli's equation. There are many different types of Bernoulli's equation, but this one deals with pressure units, which is what we're going to use to explain lift later on. Our first term in the equation is your pressure term. Obviously, being in pressure units, you have to have pressure. Next off is your kinematic energy unit in the equation, and that's defined using velocity and rho in this case, which is density. The final term is your height differential across the system that you're trying to use Bernoulli's on. That term is described by z, which is your height, and gamma, which is your specific weight. Specific weight is, of course, the gravitational constant and your density combined. Now, you can also use this to explain lift. Doing some simple algebra, we first start off by eliminating our height terms, because in our system, the height is the exact same, which is awesome because it makes things a lot simpler for us. Now, doing some quick algebra, you can reduce the Bernoulli's equation down to this simple formula. As you can see, you have a difference in pressure and a difference in velocity, give or take. Now, in order for lift to happen, this term must be positive. Same goes for this, because for one to be positive, this has to be positive as well. Now, Taylor, do me a favor and blow on this sheet of paper. In this case, pressure 2 and velocity 2 are on the top sheet of this paper, and pressure 1 and velocity 1 are on the bottom sheet of this paper. Now, Taylor is going to blow on the top of the sheet of paper. As you can see, the paper stays elevated even though my hand is not there. In this case, Taylor is putting a velocity 2 over the top, which is greater than velocity 1, which in this case is 0. In this case, pressure 2 is also atmospheric pressure, and pressure 1 is atmospheric pressure, and pressure 2 less than atmospheric pressure based on this equation. And that's how lift works.
Awesome. Well, we greatly appreciate your time with us today here, Professor. Thank you. Professor Moore.
You're welcome.
Just for a quick recap, from this equation he reduced from Bernoulli's, pressure drop causes a velocity. Higher velocity at the top, lower pressure on the top, higher pressure on the bottom, and we get lift. Now, we have Caroline and Professor Sophia all the way from Venezuela.
Take it away, Caroline.
Thank you, Taylor. So now we're going to have Professor Sophia just continue the discussion we were just having with Professor Moore.
So if you look at this wing, air is going to have to travel a longer distance over the wing, and since it's traveling longer, it has to compensate that by having greater velocity, and since the velocity is increasing, the pressure has to drop. But the thing is, it's dropping below atmospheric pressure. The pressure below the wing, it's an atmospheric pressure, therefore that difference in pressure is what causes the lift.
So, but then what difference would this shape have with like maybe a flat wing?
Well, if you can see here, the difference in distance they have to like cover. So here it's not such a long distance, therefore it doesn't have a lot of velocity to compensate for. So it's not such a big pressure drop, therefore not much of a lift. And also, as you saw with Professor Moore, with his experiment, you gotta control where the air is coming from in a flat wing, so you have to blow over it to create the lift. Whereas with this shape of wing, we don't take that in consideration.
Oh, that's really nice. But then how does this really help a plane fly, like in the real world?
Well, the wings and the lift of the wings will help the plane stay elevated, and there can also be control. So for example, when they land, they change the orientation of the wings and like things like that when they turn and when they want to go up and down. So the wings change their orientation as much as where the plane wants to go.
Well, thank you so much for your
You're
time.
welcome.
To recap, we have the shape of the wing like this for a real plane instead of a flat wing because you can't really control in real life where the air flows. So then you need to have an optimization for the velocity on top, which will create more lift.